Driven by way of the unquenchable side interest to investigate the mysteries and procedures of the universe, humankind has embarked on an experience that opposes the limits of time, searching for replies to the inquiries that balance out the texture of truth. Strikingly, the James Webb Space Telescope, with its penetrating eye, has caught a brief look at a grandiose design that goes before the start of stars, a divine irregularity that appears to be more seasoned than the actual universe. You are altogether likely thinking, how can a structure be more seasoned than our universe? Is the Big Bang Theory inaccurate? As we find how the James Webb Telescope just recognized a 13.8 billion-year-old structure and its extensive ramifications, consider taking a gander at the tremendous vast domain where stars and systems complete a shocking dance of light and gravity, uncovering the mysteries of the past and what's to come. That is precisely what the James Webb Space Telescope, an astonishing space probe, does daily, capturing and communicating its stunning discoveries back to Earth. It has revealed a perplexing exhibition, a 13.8 billion-year-old heavenly shape that opposes the very underpinnings of our vast understanding. Through this super-technological marvel, we are confronted with a significant cosmic thrill ride. A thrill ride that is unpredictably woven into the very fabric of space itself. This shocking disclosure has ignited a typhoon of discussions and debates within the scientific community as they attempt to get to the bottom of this enigmatic structure. For many, researchers and great observatories all over the planet are consistently overwhelmed with questions regarding this perplexing peculiarity. The most popular among these inquiries is, how could the James Webb Telescope see a structure that is more ancient than the universe itself? To respond to this question, we need to first focus on this structure. It is not merely a world, a cloud, or a black hole. It is a star, a very unique and distinctive star. It is situated more than 200,000 light-years away, near the constellation Libra. It is referred to as HD 142283, yet it has a truly fitting name, the Methuselah star, after the biblical figure who lived for a remarkably long time. This star is not only ancient but also incredibly fast. It zooms through space at a speed of more than 800,000 kilometers per hour, revealing its dramatic details some 12 billion years in the past, while the precursor of our Milky Way galaxy engulfed a dwarf galaxy that became its unique home. However, what makes the Methuselah star truly intriguing is not its speed but its age. It is one of the oldest heavenly objects we have observed, and its age defies logic. According to the initial estimates, the star was about 16 billion years old, but the most current estimate is 14.46 billion years, with a margin of error of 0.88 billion years. This estimate represents a puzzle because the age of the universe, determined from observations of the cosmic microwave background, is around 13.8 billion years. How could a star be older than the universe itself? It seems implausible. This conundrum has led to questions about the star's age, the universe's age, or the accuracy of the measurement methods. Could the star be a remnant from a previous universe? Should the universe be older than we suspect? Could our measurement techniques be flawed? We need to explore these possibilities. Firstly, we need to consider that estimating the age of heavenly objects is a complex technical challenge. Stars like our Sun maintain their brightness, temperature, and size for billions of years, making age estimation difficult. Astronomers rely on subtle changes in brightness and color over time and compare these measurements to theoretical models that predict how stars evolve with age, a method known as stellar evolution. Another marker of a star's age is its magnetic activity. Magnetic activity, such as flares and bursts of energy on a star's surface, decreases as a star gets older. Astronomers have developed advanced methods, including astroseismology, to observe vibrations on a star's surface caused by waves traveling through its interior. These vibrations help estimate the star's age more accurately. For example, using this method, astronomers have estimated the Sun's age to be around 4.58 billion years. Returning to the Methuselah star, astronomers assigned an age to it by considering the stellar population it belongs to. Stars within the universe can be categorized based on the number of heavy elements, or metals, they contain. Our Sun is a population I star, rich in heavy elements. In contrast, the Methuselah star is a population II star with fewer heavy elements, especially iron, suggesting that it was formed before most of these heavy elements were created in the universe, which occurred in the explosions of massive stars known as supernovae. There is also a theoretical class of stars called population 3 stars, which are believed to have no heavy elements. These stars are thought to be the first ones that formed in the primordial universe shortly after the Big Bang. They were extremely massive and hot, and they burned their fuel quickly, converting hydrogen and helium into heavier elements. When they died, they exploded as supernovae, spreading some of these elements into the surrounding space. Population 2 stars emerged from the gas clouds that had been slightly contaminated by these elements, while population I stars originated from gas clouds that had been further enriched by subsequent supernovae. The characteristics of the Methuselah star present a complicated question. How could it be older than the universe itself? The solution is not straightforward, as it involves a lot of uncertainty and assumptions. Based entirely on measurements from the Hubble Space Telescope, there is a 70% probability that the Methuselah star's age ranges from 13.6 to 30%, and a 15% chance that it is even older. Considering the variables, there is roughly a 20% chance that the star's true age is younger than the universe's age. This is akin to rolling dice and getting a 6, which is not impossible but also assumes that there are no other sources of error or bias in the age estimation. Nonetheless, it is undeniable that the Methuselah star is incredibly significant. It is the oldest star within the universe with a reasonably accurate age estimate. Instead of questioning if it could be more than 2 billion years older than its environment, we can approach the issue from a different perspective. Should it be that the universe is not as young as scientists initially believed? In fact, it is difficult to grasp the enormity of 13.8 billion years. If we compress the entire history of the universe into a single year, the Big Bang would have occurred on January 1st, and Earth might not appear until late December. Recorded human history would likely span the remaining 10 seconds of December 31st. Scientists determined the age of the universe by observing the light from stars that formed a few 100 million years after the Big Bang. As the universe expands, it stretches this light, making it redder, a phenomenon known as redshift. By measuring both the distance and the redshift of these stars, scientists can infer the age of the universe. Recent findings from researchers at the University of Ottawa suggest that the universe could be much older than previously thought, potentially around 26.7 billion years. Unique Gupta, a physics professor at the University of Ottawa, revives an old idea from Swiss astronomer Fritz Zwicky dating back to 1929. This idea posits that photons lose energy as they travel across vast distances in time. This contradicts observable redshift data, but Gupta argues that by accepting this theory along with the expanding universe, we might view redshift as a mixed phenomenon that is not solely due to expansion. Extending the universe's age might shed light on some of the star's well-established cosmological mysteries. This mystery arises from data collected by the European Space Agency's Gaia satellite, which provides accurate information about the speeds and positions of nearly 2 billion stars within the Milky Way. These precise measurements have led astronomers to reassess their estimates of stellar behavior throughout the universe. Various research teams have found that stars orbiting the Milky Way's outer disk, around 880,000 light-years from the galactic center, are traveling at an average speed of 167 kilometers per second. This is significantly slower than stars in similar outer regions of other spiral galaxies, which travel at an average speed of about 240 kilometers per second. Astronomers had expected that stars located far from the galactic center would have speeds more in line with those of stars in other galaxies. These findings have prompted changes in the scientific community's understanding of how galaxies form and evolve. Additionally, the presence of dark matter raises questions about the nature of our universe's fundamental and developmental processes. Scientists have been grappling with these questions, striving to uncover the fundamental principles governing the universe. Advances such as those made possible by the James Webb Space Telescope and the Gaia satellite have provided exceptional insights into these grand mysteries. They have allowed astronomers to explore distant corners of the universe and observe phenomena that challenge our current understanding of existence. As humankind continues its exploration of the universe, driven by curiosity and technological advancement, we can anticipate even more astounding discoveries that will reshape our perception of the universe and our place within it. The journey to unravel these secrets is ongoing, promising new revelations and deeper insights into the vast and complex universe that surrounds us. The study of the universe has been a journey marked by humankind's unquenchable curiosity and relentless pursuit of knowledge. A quest spanning centuries, driven by technological advancements and a profound desire to unravel the mysteries of the cosmos. At the forefront of this exploration are powerful tools like the James Webb Space Telescope, JWST, and the Gaia satellite, which have revolutionized our understanding of celestial bodies and cosmic phenomena. One of the most intriguing discoveries made possible by these instruments is the Methuselah star, officially known as HD 142283. This star, nicknamed Methuselah after the biblical figure known for his extraordinary lifespan, has sparked significant debate and interest within the scientific community. Initially estimated to be around 16 billion years old, which would predate the current age of the universe as determined from observations of the cosmic microwave background radiation, CMBR, Methuselah's age presents a perplexing mystery. The age of the universe is estimated to be around 13.8 billion years based on CMBR data. This discrepancy raises fundamental questions about the accuracy of our dating techniques, the nature of cosmic evolution, and the possibility of alternative explanations, such as a remnant from a previous universe or variations in fundamental constants of physics over time. To understand the age and nature of celestial objects like Methuselah, astronomers use sophisticated techniques such as astroseismology, which studies the oscillations of stars to infer their internal structure and age. This method, along with measurements of a star's chemical composition and orbital elements, provides crucial insights into their formation and evolution. Stars are categorized into different populations based on their abundance of heavy elements like iron. Population 1 stars, such as our Sun, are relatively young and rich in heavy elements, indicating they formed from enriched interstellar gas. In contrast, Population 2 stars like Methuselah are older and contain fewer heavy elements, suggesting they formed from primordial gas that had not been enriched by previous generations of stars. The discovery of Methuselah challenges our understanding of stellar evolution and the early conditions of the universe. It suggests that stars may have formed earlier than previously thought, potentially in a universe that underwent rapid changes in its early stages. This idea aligns with theories proposing that the universe might have experienced periods of accelerated expansion or variations in fundamental constants that could influence the passage of time and the age of celestial objects. Advances in observational astronomy, particularly through instruments like JWST and Gaia, continue to push the boundaries of our knowledge. These tools enable astronomers to probe deeper into space and observe phenomena with unprecedented clarity and detail. For example, Gaia's precise measurements of star positions and velocities have provided new insights into the structure and dynamics of our Milky Way galaxy, revealing unexpected patterns in stellar movements and the distribution of dark matter. Dark matter remains one of the most enigmatic substances in the universe, accounting for a significant portion of its mass while eluding direct detection. Its presence is inferred from gravitational effects on visible matter and the motions of galaxies and galaxy clusters. Understanding dark matter is crucial for comprehending the large-scale structure of the universe and the formation of galaxies, including our own Milky Way. Recent observations from Gaia have shown that stars in the outer regions of the Milky Way move at slower velocities than expected compared to stars in similar regions of other spiral galaxies. This discrepancy suggests that our galaxy may have a different,